Hi everyone, welcome back to another lesson of our DSA lesson series. So today we are talking about all pair shortest path problem. Imagine you have a weighted graph. In a standard single source shortest path problem, you pick one vertex as a starting point and find the shortest distance to every other node. But in all pair shortest path problem, we want to find the shortest distance between every possible pair of vertices in the graph. For example, if we have 4 vertices, we need to find the shortest path from 1 to 2, 3 and 4. Then from 2 to 1, 3 and 4 and so on for every vertex. Here, you might think that can't I just use the Dijkstra's algorithm? Well, Dijkstra is a single source shortest path algorithm. To find all pairs, you would have to run Dijkstra once for every vertex in the graph. If there are 4 nodes, you will have to run it 4 times. Instead, the Floyd-Warshall algorithm gives you the shortest distance between every pair of vertices in a single execution. It follows a dynamic programming approach, which means it breaks a complex problem into simpler subproblems in a recursive manner. Another massive advantage with this Floyd-Warshall algorithm is that it works on graphs with negative edge weights. Dijkstra only works with positive weights and will give you the wrong result if a negative edge exists. If you have negative weights, you need either Floyd-Warshall or the Bellman-Ford algorithm. So the core idea is simple. We look for a shorter path between two vertices by going through an intermediate or middle vertex. Suppose there is a direct edge from vertex 1 to 2 with a weight of 9. Floyd-Warshall checks if going from 1 to 3 then 3 to 2 is shorter than the direct path. We repeat this process by considering every vertex as a potential middle element. So now let's look at a simple example so you guys can understand this concept easily. First, let's look at the working principle of this. Suppose that you have to find the shortest distance between 1 to 2. So there is this direct path, and also it's possible that we can go to 2 via 3. 1 to 3, 3 to 2, and via 4. 1 to 4, 4 to 2. And sometimes these paths can have shorter distance rather than the direct path. So in our example here, what you're going to do is that first we will take the 1 as middle element and find all the shortest distance between every pair of vertices. Then we will take 2, 3 and 4. So first what we have to do is that first we have to create the initial distance matrix. So yeah, here my matrix is 4 by 4 one because I have 4 vertices. If you have 6 vertices, it will be 6 by 6 matrix. First all the diagonal elements will be 0 because distance from a vertex to itself is always 0, right? So 1 to 1 will be 0, 2 to 2 will be 0, likewise 1 to 1 will be 0, 2 to 2 will be 0, 3 to 3 0, 4 to 4 0. Okay, and also we can fill out the direct paths, and if there is no direct path between two vertices, it will be infinity. Alright, so first 1 to 2, 1 to 2 we have 9. Okay, 1 to 3, 1 to 3 minus 4. 1 to 4, 1 to 4, there are no any direct paths, so we will put it as infinity. 2 to 1, 6. 2 to 3, no direct path, so it will be infinity. 2 to 4, 2. 3 to 1, no direct path, it will be infinity. 3 to 2 5. 3 to 4, no direct path, it will be infinity. 4 to 1, no direct path, it will be infinity. 4 to 2, no direct path, infinity. 4 to 3, 1. Now we have created our initial distance matrix. Then we can move to the D1 matrix, which will assign 1 as the middle element, right? So to create the D1 matrix, you have to refer the D0 matrix. Okay, so by referring the initial matrix, you will create the D1 matrix. So this will be the base matrix which will contribute in creating the D1 matrix. Okay, so here first we will get the diagonal 0, as we know. 0. Alright. So what you have to do is that first you know that in the D1 matrix the middle element is 1. So from the D0 matrix, get the column of 1 and the row of 1. This will be our working column and working row. So fill out those accordingly. 6. Infinity. Infinity here. Then 9 minus 4, infinity. 9 minus 4, infinity. Okay, now we have to fill out the 2 to 3. So in the D0 matrix, 2 to 3 is as you can see, it's infinity, but here we take the middle element as 1. So going from 2 to 3, we will do it as first we will go from 2 to 1, then 1 to 3. Alright, so 2 to 1 is 6, 1 to 3, 1 to 3 is minus 4, so it will give us answer as 2. So 2 is less than infinity, so we will add 2. Right, then 2 to 4, so 2 to 4, 2 to 4 is 2. Here we have 2. Then by taking 1 as the middle element, we can get 2 to 1 plus 1 to 4. Right, so 2 to 1 is 6. 1 to 4, 1 to 4 is infinity, so it will be infinity. So 2 is less than infinity, so we will take 2 here. Alright, then we have to solve 3 to 2. So 3 to 2, 3 to 2 is 5. By taking 1 as the middle element, we take 3 to 1 plus 1 to 2. Alright, 3 to 1 is infinity, 1 to 2, 9. So it will obviously become infinity. So 5 is less than infinity, we will take 5. 5 here. Then we have to find 3 to 4. 3 to 4. 3 to 4 is infinity. 3 to 1. Then 1 to 4. 3 to 1 is again infinity. 1 to 4, it's also infinity, so answer is infinity. Okay, now we have to find 4 to 2. 4 to 2 4 to 2 is infinity, and if we take middle element as 1, we will get 4 to 1 plus 1 to 2. All right, 4 to 1 infinity, 1 to 2 9, so it gives us again infinity. All right, then we have to take 4 to 3. 4 to 3, here 4 to 3 is 1, we have put it. Then if we take 1 as the middle element, we will go from 4 to 1, then 1 to 3. So 4 to 1 is infinity, 1 to 3, 1 to 3 is minus 4, so it will become infinity. So 1 is less than infinity, so we will take 1. Okay, now we have created our D1 matrix. Now we will fill out the D2 matrix, where the middle element is 2. So what we have to keep in mind is that when we filled out the D1 matrix, we referred D0 matrix, right? So when we are filling out D2 matrix, we have to refer D1 matrix. All right, so first since the middle element is 2 here, we will set our working column and working row as 2 in the D1 matrix, just like that. Okay, first we will fill out the diagonals. As we know, it's 0, 0, 0, 0. Then we will fill out the working row and working column, which will give us 9, 5 infinity, 9, 5 infinity, 6 to 2, 6 to 2. All right, now first we have to calculate 1 to 3. So 1 to 3 in the D1 matrix will be minus 4. So since we are getting the middle element as 2 here, we have to calculate 1 to 2, then 2 to 3. 1 to 2 is 9, 2 to 3 is 2, so answer is 11, but minus 4 is less than 11, so we will choose minus 4. Minus 4. Then we have to choose 1 to 4. Okay, 1 to 4 is infinity, but by getting the middle element, 1 to 2 plus 2 to 4, 1 to 2 is 9, 2 to 4 is 2, so answer is 11. So 11 is less than infinity, so we will choose 11. 11 goes here. All right, then we have to find 3 to 1. So 3 to 1, 3 to 1, 3 to 1 is infinity. By getting the middle element, we have a path 3 to 2 and 2 to 1. So 3 to 2 is 5, 2 to 1 is 6, so answer is 11. So 11 is less than infinity, so we will choose 11. 11 goes here. Then we have 3 to 4. 3 to 4 is infinity. Our middle element path is 3 to 2 to 2 to 4. 3 to 2, 5. We have put 5 here. 2 to 4. 2 to 4 is 2. So answer is 7. 7 is less than infinity. So we put 7. goes here. Then we have to find the 4 to 1. 4 to 1 here is infinity. The middle element path is 4 to 2 to 2 to 1. 4 to 2, 4 to 2, 4 to 2 is infinity. 2 to 1, 2 to 1 is 6. So it will become infinity. Since both sides are infinity, we will add infinity here. Okay. Then we have to find the 4 to 3. 4 to 3, 4 to 3 is 1. The middle element path is 4 to 2 and 2 to 3. So 4 to 2 will be infinity. 2 to 3, 2 to 3 will be 2. So it will be infinity. So 1 is less than infinity. We will add 1 as our shortest path. Okay. So now we have created our D2 matrix. Then we can move to creating our D3 matrix, where we choose the 3 as middle element. So as I mentioned before, to fill out D1 we refer D0, to fill out D2 we refer D1, to fill out D3 we will refer D2. So since we are choosing 3 as the middle element here, I will set the working column and working row as 3. Okay. Alright. First we will fill out the diagonal, which we know is 0 obviously, because distance from a vertex to itself is always 0. Okay. Then we will fill out the working column and working set. We have -4, 2, then 1. Then we have 11, 5, 7. 11, 5, 7. Now let's continue to fill the D3 matrix. So first we have to find out 1 to 2. 1 to 2 is 9. Our middle element path is 1 to 3, then 3 to 2. 1 to 3 is -4, 3 to 2 is 5. So answer will be 1. So 1 is less than 9, so we will choose 1. Alright. Then we have to find 1 to 4. 1 to 4 is 11. Our middle element path is 1 to 3 plus 3 to 4. 1 to 3 is -4. 3 to 4 is 7. So we will get 3. So 3 is less than 11. So we will add 3 as our distance here. Okay. Now we have to find 2 to 1. 2 to 1 is 6. Our middle element path is 2 to 3, then 3 to 1. 2 to 3 is 2. 3 to 1 is 11. So answer will be 13. So 6 is obviously less than 13. So we will add 6 as our distance. Okay. Then we have to find 2 to 4. 2 to 4 is 2. Then our middle element path is 2 to 3, then 3 to 4. 2 to 3 is 2. 3 to 4 is 7. So the answer is 9. 2 is less than 9, so we will add 2 as the shortest distance. Okay. Now we have to find 4 to 1. 4 to 1. 4 to 1 is infinity. Our middle element path is 4 to 3, then 3 to 1. 4 to 3 we have 1. 3 to 1, 3 to 1 we have 11. So it's 12. 12 is less than infinity, so we will add 12. Okay. Then we have to find 4 to 2. 4 to 2 is infinity. Our middle element path is 4 to 3, then 3 to 2. 4 to 3 is 4 to 3 is 1, 3 to 2 is 5, so answer is 6. 6 is less than infinity, so we will add 6. Alright. Okay, now we have created our D3 matrix also. So now we can move to our final matrix where we choose 4 as our middle element. Okay, as the previous ones, to fill out the D4 matrix we will refer D3 matrix. Since we choose the 4 as our middle element, we will set the working column and working row as 4 here. Alright, now first I will fill out the diagonal. Okay, then the working row and working column 3 2 7. Then 12 6 1, 12 6 1. Okay, now let's fill out this matrix. Here first we have to find 1 to 2. 1 to 2 is 1. Our middle element is 4, so our path will be 1 to 4, then 4 to 2. 1 to 4 is 3, 4 to 2 is 6, which will give us 9, so 1 is less than 9. We will add 1 here. Okay, then we have to find 1 to 3. 1 to 3 we have -4. Our middle element path is 1 to 4, then 4 to 3. 1 to 4 we have 3 here. 4 to 3 we have 1, so answer will be 4. -4 is less than +4, so we will add -4. -4. Now we have to find 2 to 1. 2 to 1 we have 6. Our middle element path will be 2 to 4, then 4 to 1. 2 to 4 is 2. 4 to 1 is 12, so answer will be 14. So 6 is less than 14, so we will add 6. Okay, then we have to find 2 to 3. 2 to 3 we have 2 here. Our middle element path is 2 to 4, then 4 to 3. 2 to 4 is 2, 4 to 3 1, answer is 3, but 2 is less than 3, so we will add 2. Okay, then we have to fill out 3 to 1. 3 to 1, here we have 3 to 1 we have 11. Our middle element path is 3 to 4, then 4 to 1. 3 to 4 is 7, 4 to 1 is 12, so we will get 19 as our answer, but 11 is less than 19, so we will add 11. So now we have to find 3 to 2. 3 to 2 is 5. Our middle element path is 3 to 4, then 4 to 2. 3 to 4 is 7, 4 to 2 is 6, 7 plus 6 13. So 5 is less than 13, we will add 5. So now we have filled out our fourth and final distance matrix, which will give us the shortest distance between every pair in our graph. So we have 4 distance matrices, D1, D2, D3 and D4, except for the our initial distance matrix. So suppose that you have n vertices in your graph, so you should have n distance matrices. All right, I had 4 vertices here, so I have 1 2 3 4 distance matrices except for the initial distance matrix. I hope you got an understanding about this process clearly. So now let's move into the formula that makes up this process. Now let's write the formula for this. Okay, we will take these positions as I and j. Okay. Here it's the D4 matrix, here it's the D3 matrix, so dk will become dk minus 1. Still the values for the positions are same. Here we have 3 1 and here also we have 3 1, so we will add I j. Now this one is also d3 dk minus 1. But here we have the I position, yeah, it's okay, and we have 4 here, so for the 4 we used k, so we use I k. Okay, here plus d k minus 1 4 is k, 1 is j. Right, so this is the formula, but since we are choosing minimum from this and this, we will add this function. Alright, that is a wrap on the Floyd Warshall algorithm. As we have seen, this dynamic programming approach allows us to solve the all pair shortest path problem in just a single execution. By systematically using each vertex as an intermediate node, the algorithm finds the shortest distance between every possible pair of vertices in the graph. Remember, while Dijestra's algorithm is a great choice for the positive weights, Floyd Warshall is essential when your graph contains negative edge weight. It's most efficient for dense graphs where most vertices are connected. If you found this video valuable, like, share, subscribe and click the bell icon to be notified for more videos. Thanks for watching.